Did you know that 1,000,000 kilometers from Earth, a machine is looking back in time? Literally. The James Webb Telescope is peering 13 billion years into history, and its findings have left scientists in controlled panic. Webb is showing us massive, fully formed galaxies where we expected only dust and infant stars. The data is right, but our models are suddenly very wrong. It is forcing us to confront a possibility that the story we have been telling ourselves about the universe is missing something fundamental. Organize your production at CRA.ai Spacer with code SPACE, powered by today's sponsor, Cray.ai. We are finally seeing the universe as it is. Thanks for watching, and as always, Allah Hafiz. To understand why Webb's findings are so shocking, we have to look at the theory that has dominated our thinking for decades: lambda, cold, dark matter. This standard model is built on 3 pillars: the Big Bang, the expansion starting 13.8 billion years ago, dark matter, the gravitational scaffolding, and dark energy, the force accelerating it all. Webb was built to test this model. With its 6.5-meter golden mirror, it captures infrared light, the only light capable of reaching us from the dawn of time. Because the universe is expanding, light from the first galaxies has been stretched, or redshifted, into the infrared. To see the beginning, we must see in infrared. Scientists had a clear set of expectations. They thought they knew what the early universe should look like, but when the first images arrived in July 2022, they saw something else entirely. The excitement was soon tinged with unease. The galaxies weren't infant dust clouds, they were massive and mature. The panic had officially begun. In our next chapter, we'll dive into the specific galaxies that are breaking our math. Stay curious, and as always, Allah Hafiz. Orbiting nearly 1.5 million kilometers from Earth, the James Webb Space Telescope is doing something no instrument in history has ever achieved. It is looking back in time. Webb was built to test the standard model of cosmology: lambda, cold, dark matter, a theory built on the Big Bang, dark matter, and dark energy. According to this model, galaxies grow slowly through hierarchical assembly, small structures merging over billions of years into the giants we see today. In the first few 100 million years, the universe should be populated only by small, irregular seeds. There simply hasn't been enough time to build anything else. This is what the standard model predicts, and it is not what Webb is finding. Instead, we are discovering galaxies that are extraordinarily massive. We are seeing structures comparable to the Milky Way existing at epochs when the universe was only a few 100 million years old. These galaxies should not exist. Early observations found an excess of bright red galaxies at redshifts of 10 and beyond, luminous, well-developed, and terrifyingly massive. At first, researchers were cautious, but as spectrographs confirmed these distances with precise measurements, the problem didn't go away. It got worse. Total stellar mass in the early universe is 10 to 100 times higher than predicted. Astronomers have a name for them: impossibly massive galaxies. Managing impossible data requires precise operations, like those powered by today's sponsor, Cray.ai, your partner in production efficiency. From merch shops to detailed workflows, Cray.ai manages the chaos. Start for free at CRA.ai Spacer and use code SPACE. Within the assumptions of the standard model, these galaxies are a physical impossibility. Our story of how the universe grew is missing something fundamental. Is our understanding of gravity wrong, or is dark matter behaving in ways we never imagined? We are rewriting the first billion years of cosmic history. We are finally seeing the universe as it actually is. The panic in the community isn't just about failure, it's about the birth of a new understanding. 13 billion years of history, and we're finally reading the real story. Join me in the comments to discuss what comes next. Thanks for watching, and as always, Allah Hafiz. We'll see you in the next one. The reaction to these findings has been fascinating. In science, the unexpected is usually a cause for celebration, but alongside the excitement, there is a deep sense of unease. If our standard model cannot explain these massive galaxies, one of 3 things must be true. Each possibility represents a potential revolution in our understanding of physics. In our standard models, star formation is an inefficient process, regulated by feedback. Supernovae and black hole outflows usually blow away the gas before stars can form. But what if early galaxies were different? What if they formed in a burst mode, converting gas into stars with near-perfect efficiency before feedback could take hold? This burst theory is physically plausible, but it pushes the very limits of what we think is possible. It's a challenge to every model of star formation we have. Alternatively, the dark matter halos themselves might be much more massive than we predicted. This would require us to rethink the very first fraction of a second after the Big Bang. Whether it's star formation or the nature of gravity itself, we are finally seeing the universe as it is. We are rewriting the first billion years of cosmic history. The real story of our origins is far more complex than we ever imagined. Join the discussion below, stay curious, and as always, Allah Hafiz. Another clue lies in the stars themselves. To measure a galaxy's mass, we must first understand its light. But luminosity and mass aren't always what they seem. This is the initial mass function, the recipe that tells us how many small versus large stars form from a gas cloud. For decades, we've used the same recipe for every galaxy. But what if the early universe used a different recipe? A top-heavy model, where gas conditions produced far more massive, bright stars than we see today. If the early universe was top-heavy, a bright galaxy might actually be much lighter than we think. We might be overestimating their mass by assuming the recipe never changed. This could resolve the tension, but the correction needed is massive. And right now, our data on the early IMF is still very limited. We are guessing at the recipe. We are rewriting the history of how stars are born. Whether it's the recipe or the math, we are finally seeing the universe as it is. 13 billion years of history, and we're just finding the right tools to read it. Join the discussion below. Stay curious, and as always, Allah Hafiz. The most unsettling possibility of all is that the problem lies not in the stars, but in the foundations of our universe, the underlying cosmological model itself. Our model assumes the universe began with a specific pattern of density fluctuations. These primordial ripples are the seeds that gravity grows into galaxies. If there was more power at small scales than we thought, dark matter halos would form earlier and be more massive. This would explain Webb's impossible galaxies perfectly. This points to a modification in the inflaton field, the force that drove the Big Bang. We are testing the dynamics of the universe's very first moment. Webb is providing a direct observational window on the physics of inflation. This would be one of the most extraordinary scientific discoveries of all time. We are no longer just looking at galaxies. We are looking at the mechanism that created everything. We are rewriting the story of existence. 13 billion years of history, and we're finally reading the real story. Thank you for joining this journey. Stay curious, and as always, Allah Hafiz. Webb has found another anomaly that is giving scientists pause. Not just massive galaxies, but structured ones. Well-ordered, mature galaxies where we expected only chaos. In our standard models, the early universe was a violent place. Galaxies were born from messy mergers and high-speed collisions, leaving them irregular and disturbed. But Webb is finding organized disks and coherent rotation in the first billion years. These young galaxies look disturbingly similar to the mature spirals of our nearby universe. One possibility is that disk formation is simply more robust than we thought, that gas cools and settles into a rotating configuration much faster and more efficiently. But a more provocative idea is that our entire picture of violent assembly is wrong. Perhaps galaxies form gently, through smooth accretion along cosmic filaments. If this is true, it requires a complete revision of galactic evolution. We are discovering a universe that is far more efficient at creating order than we ever imagined. The data is changing everything. Join the discussion below on the nature of order in our cosmos. Stay curious, and as always, Allah Hafiz. At the heart of nearly every large galaxy lies a supermassive black hole, 1 billion times the mass of our Sun. Usually, these giants take billions of years to grow. But Webb is finding supermassive black holes in the very early universe, disturbingly large ones, existing at a time when they simply haven't had enough time to form. These active galactic nuclei are powered by black holes that are already billions of solar masses. Within our standard models, this is extremely difficult to explain. How did they get so big so fast? One theory is direct collapse, where massive gas clouds bypass star formation to create unusually large black hole seeds. Another possibility is super-Eddington accretion, growth that exceeds the theoretical speed limit. Webb is pushing these optimistic models to their absolute breaking point. As with the massive galaxies, the implication is clear. Our understanding of how structure forms in the early universe is fundamentally incomplete. The data is rewriting history as we speak. Join the discussion below on the mystery of the first black holes. Stay curious, and as always, Allah Hafiz. Beyond massive galaxies and black holes lies a discovery that strikes at the very geometry of our universe. It concerns the rate of expansion itself, the Hubble constant. The Hubble constant determines the age, size, and ultimate fate of everything we see. It is the single most fundamental number in all of cosmology. But there is a problem. Ancient light from the Big Bang gives us one answer, while nearby stars give us another. These two numbers should be identical. Instead, they disagree by 9%. To solve this, Webb used its infrared power to look at Cepheid variables, pulsating stars that act as calibrated distance markers across the cosmos. Webb can reach further than any telescope before it. Scientists hoped that with Webb's precision, the discrepancy would vanish. Instead, the tension has only become more robust. Webb's data confirms that the distance ladder value remains high. The Hubble tension is now essentially impossible to explain away as a simple measurement error. Something is fundamentally wrong. Our standard model cannot explain both measurements at once. We are facing a crisis in our basic understanding of reality. 13 billion years of history, and the math no longer adds up. What do you think is missing from the universe? Stay curious, and as always, Allah Hafiz. All these anomalies, the massive galaxies, the black hole enigmas, the Hubble tension, have created a crisis in cosmology, but it is also a golden age of discovery. We are looking at new physics, modifications to gravity, dark matter, and even the force of inflation itself. But Webb has one more discovery that is perhaps the most profound of all. Webb is probing the atmospheres of worlds orbiting distant stars. By measuring the fingerprints of starlight, we can now search for the chemical signatures of life. Take K2-18b, a Hyson world 120 light-years away. Webb has detected carbon dioxide and methane, consistent with a world covered by a global ocean. Most controversially, Webb found a tentative signal of dimethyl sulfide. On Earth, this molecule is produced almost exclusively by marine life. It is a potential biosignature. Exploring the unknown requires precision. Today's series is powered by Cray.ai. Organize your production workflow at Cray.ai spacer with code space. Now, the final verdict. The question of whether we are alone is no longer just philosophy. It is an empirical one, being answered with real data. We are standing on the edge of a discovery that will change everything. 13 billion years of history, and we're finally reading the real story. Thank you for joining Space Race for this journey. Stay curious, and as always, Allah Hafiz. The unease we feel is not the unease of failure. It is the unease of standing at the threshold of something new, something the existing frameworks cannot contain. Throughout history, when data outran theory, revolutions occurred. Moving the Earth from the center didn't destroy astronomy, it transformed it. Relativity didn't destroy physics, it elevated it. Now, Webb presents us with impossible galaxies, impossible black holes, and an expansion rate that refuses to add up. These are the data points for our next great revolution. Now, Webb presents us with impossible galaxies, impossible black holes, and an expansion rate that refuses to add up. These are the data points for our next great revolution. With enough fuel for 20 years, Webb will observe millions of galaxies and characterize hundreds of worlds. It is pointing us toward a frontier where the maps run out. The universe is holding secrets, and Webb is finding them one by one. We are living through the beginning of a revolution. The cosmos has never been boring. Thank you for joining Space Race for this epic journey into the unknown. I'm so glad we explored the start of everything together. Stay curious, and as always, Allah Hafiz.